do a few practice problems. So what is the product of the following reaction? So I've got this alkane here, and I've got bromine and heat. So I know, okay, an alkane, Br2 in heat or Br2 in light, that's going to do a halogenation reaction, a radical halogenation reaction. Now I know that because I've memorized it kind of, and maybe now you understand it, that bromine is highly selective. So it's going to go for the most substituted carbon that has a hydrogen. So here I have a quaternary carbon, but of course quaternary carbons don't have hydrogens on them. So I'm not going to put a bromine there, that wouldn't make sense. So the next most substituted position I have is this tertiary position, and there is a hydrogen there. Okay, there are no other tertiary positions. All we have left are secondary positions and primary positions. So this is definitely the best position for the bromine to go to. So I mean, as a test, what you can do is you guys can write out the initiation step for this, the propagation steps, and the termination steps for this reaction. That would be a good exercise for you guys to do. But in terms of getting the answer for this, it will be pretty simple. All we're going to do is put a bromine right there. Okay. Now, technically, you might have a professor that cares about stereochemistry. Stereochemistry here is not specific, so you will have some molecules where the bromine is on the wedge in this case, and you'll have some molecules where bromine is on the dash. Okay? What is a side product of the following reaction? So here I know, okay, I've got my alkane, I've got light and Br2. So this is a radical halogenation reaction. And the most substituted position is the secondary positions here and here, right? And they're actually identical, so it doesn't matter which one I choose. So my product for this will look like this, where I have a bromine on one of those carbons. And it doesn't matter which one because they're identical. But that's, you know, this is the product, the desired product. But that's not what the question asked for. The question asked for the side product. And I know the side product is the termination step where I have two of my alkane radicals reacting together. So in order to figure out what my side product is, I have to figure out what my alkane radical looks like and then just put two of those together. So if my bromine ends up here, then I know I used to have a hydrogen there, right? And my bromine radical in my first propagation step met with one of the electrons to the hydrogen, which means this electron went on to the carbon. In other words, my radical alkane looked like this, where there was a radical electron right there. So now that I know what my radical alkane looks like, I just have to put two of these together. And remember, the easiest way to go from the radical molecules to the product is to draw it so that the radical electrons are facing each other, okay? So I'm going to draw this molecule twice where the radicals are facing each other. So that'll look something like this. There's one of those radicals and this. Okay, so this radical plus this radical can lead to, well, basically, we're just going to form a bond right there, where these two electrons are going to be in that bond. And so my product is going to look exactly like this, but with that bond there. So if I actually draw that out, it would look like this. So do I have an answer choice that looks like this? Yes, I do. It's flipped on its side compared to the way that I drew it, but that is answer choice A. So answer choice A is the side product of this reaction. Okay, so the next question is how many potential products are possible from the monochlorination of 3,3-dimethylpentane? So I've drawn 3,3-dimethylpentane here, which, you know, I assume that you guys would do that without looking at it. But anyway, I forgot to erase it, but that's fine. So there's 3,3-dimethylpentane. Now, we can add 1 chlorine to this molecule through radical halogenation. The question is, where can it go? Now, for chlorination, we know that chlorination is much less selective than bromination. Okay, bromination, you're almost going to get all of your product going to the most substituted position where a hydrogen exists. For chlorination, you're going to get pretty much anywhere where there is a hydrogen, you get the possibility of a chlorine there. Now, of course, you're going to get more products where there's a more substituted hydrogen, but you will still get products in less substituted positions. So what we're going to do in this problem is we're going to look at all the possible places where the chlorine could go. Okay? So the first thing I'm going to do is I'm going to label the chemical equivalent carbons, okay? So for example, what do I mean by that? If I call this carbon A, is this next carbon here, is that the same as carbon A, or is that a different carbon in a different environment? Well, it's definitely in a different chemical environment because carbon A is a methyl group, but this carbon here, which we're going to call carbon B, is a methylene group. Okay, so it is different. It is not chemically equivalent. Okay, so then what about this next carbon? Is this carbon the same as A or the same as B, or is it a new carbon that is chemically distinct from the others? Well, the answer is it is new. It is different from A and B, and so we will call it carbon C. Okay, now this carbon is actually identical to carbon B, so we will name it carbon B, which means this last one over here is identical to carbon A. Now these two carbons are distinct from all the others, so let's call those D. But they are identical to each other, so we're going to call both of them D. Okay? So now we have to figure out of all of these, A, B, C, and D, okay, which ones have hydrogens on them. So let's change color. So is there at least one hydrogen on carbon A? Yes, in fact there's 3, but we only need at least 1 to do monochlorination. Okay, what about B? Does carbon B have at least 1 hydrogen? Yes, it has 2, but that's fine, it has at least 1. All right, carbon C. Does carbon C have at least 1 hydrogen? No, it does not. Okay, so we'll never be able to put a chlorine there. And let's look at carbon D. Does carbon D have at least 1 hydrogen? Yes, it's got 3, so we'll just draw 1 of them. Okay, so in all 3 of these places, A, B, and D, we can have a chlorine replace the hydrogen that I've drawn. So one of these products will look like this. Let me copy this. Okay. So there's one instance where you could have a chlorine replace hydrogen A, or we could have an instance where the chlorine replaces hydrogen B, in which case it would be here. Or we could, we could have the instance where a chlorine replaces hydrogen D, right there, in which case we will get like that. So those are the three possible products. If I draw a chlorine over here instead, I will just be redrawing this molecule, okay? If I draw the chlorine getting added to this carbon, I'd be redrawing this molecule. And if I added the chlorine getting drawn to this carbon, I'd be redrawing this one. So we don't want to draw the same molecule twice, okay? Otherwise, we'd be counting it twice. So in this case, there are only three possible products that we could form from the monochlorination of 3,3-dimethylpentane. So the answer is A.